Hello everyone, good evening. Today we see a very beautiful theorem about system of linear equation. So here is the theorem. A system of equation definitely linear system of equation Ax equal to b is consistent if and only this is the necessary and sufficient condition. The rank of A is equal to the rank of augmented matrix. So using this theorem we can decide a given system Ax equal to b will have a solution or not. That only we can decide. But from this theorem we cannot write down the explicit solution of the given system. Now here two term is very important. The first term is consistent and the second concept is rank. So consistent means actually the system has at least one solution. That is very clear definition and very easy. Now the main part is rank because the whole theorem depends on the rank. So to prove this theorem we need to understand what do we mean by rank of a matrix and how do we calculate it. So first few minutes we will spend to understand the rank and then we come back to the main theorem here. So let first discuss about the rank. So rank of a matrix. So let's say we have a matrix M and suppose the matrix having the column, I am just writing this way that alpha 1, alpha 2, dot 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 alpha. It has n column. So here alpha I belongs to I. Or let's say Fm. F is the field corresponding. We can consider here the set of all complex number in the place F. Now, once we have this n vector inside Fm, we can immediately consider the space that generated by this. So that we call the column space of the given matrix of M. We normally denote it C bracket M, and it is defined as a span by this alpha 1 vector, alpha 2 vector, alpha n vector. So basically rank means the vector space span by, so the column space means basically the space spanned by the column of the matrix M. Now see, this is a subspace of a finite dimensional vector space. It is clearly the subspace of the column space of M. It is subspace notation I use like this. This is for the subspace of the space Fm. Now since Fm is a finite dimensional vector space and Cm is the subspace of Fm, so it will have a dimension. It is clear that Cm will have a dimension. Now let me define the rank. So rank of the matrix M that we denote by R bracket M. This is nothing but the dimension of the column space of M. So if you see here the definition of the rank of the matrix M, you understand that you have to first eliminate the vectors from here that will depends on the other vector. and we take the minimum amount of vectors that are linearly independent and also generate the space. So this is the computational part, we can do it. But the theoretically this is here. Fine. So this is the rank of a matrix M. So now just so since I am talking about the rank of a matrix, so I can give a process how to calculate rank. So to do that, we need to understand basically the row operation. Although here not necessary this part, but just I am including here because if you are interested in computing the rank of a matrix, then this process you can. So what we do, the operation that we apply here, interchanging row. If you have a matrix, you can interchange rows. I'm explaining here the row operation. So the similar you can do for the column operation. So if we interchange the ith row with jth row, we denote that operation by Ri interchanging Rj. So clearly, and second one will be multiplying by a non-zero constant. Multiplying by a non-zero constant lambda. So that we denote by, so if we multiplying the ith row by lambda, then we denote, so basically the ith row will be replaced by lambda ri. So every component of ith row will be multiplied by lambda, then we replace in the given matrix and we get the new matrix. And the third one will be, we select two row and the second row we will multiply by a lambda, then we will add with the first row. That I am just writing here the operation that if I select Ri and Rj, and suppose we are multiplying Ri by Rj row by lambda and replacing it here in the place of the ith row of the given matrix, then we denote it by this. The interesting fact that if you apply this row operation, so then the rank will be unchanged. And the proof is very straightforward. It will come from elementary calculation. So here that if you have A and then you apply the finite number of row operation here and you get the matrix B, here we apply the row operation. Maybe finite number of many row operation you apply here. And this implies that the rank of P will be the same as the rank of A. Now what will be the profit here that if we do that, and especially what you do that if you have the column for the matrix A, let's say alpha 1, alpha 2, alpha n, and this is the A matrix, and let's say applying the row operation, we get the matrix B and having the column, let's say beta 1 dot beta n. Then actually the basis for the column space of A will be the same, will be the column space of the B. So what I'm meaning that if the columns of A are not easy to handle, but after applying row operation we can easily handle this beta 1, beta 2, beta n. So that we are called the Gaussian elimination process. That is called the Gaussian elimination process. Elimination process. So that basically what we'll do here, that if you have a matrix A, let's say I'm taking this type of rectangular matrix, then after applying row operation, so here you have entry every position, so this place, every place you have Now row operation here apply. Then what should we get here? That we can convert it into a matrix of upper triangular form. So here will be entry, but this place will be 0. So now this matrix is easy to handle. We can understand the column very properly, comparable with the given matrix. Now, so that's why this operation allow us to understand the basis element for the column space of it. Now some terminology we have here, that pivot position and free variable, that if you read then you can see. But this is the whole game of this process. If you have a matrix, how do you calculate rank? By calculation. This is the process. Now, yeah, everything is about the rank here. Now what we can do, that we can come back to the main theorem that we have here. So let's start. So what we can do for the proof, so it has two parts. One is the from condition we will check that is sufficient for here, and if it is having solution, then that is the necessary. So first assume that, so the solution, or maybe here the proof, because it is a theorem. So assume that A matrix at the column alpha 1, alpha 2, dot 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 alpha n. This is the A matrix, and definitely augmented matrix will be what? That alpha 1, there will be alpha 1, alpha 2, alpha n, and the extra column we get from the B. So that I am writing here B vector because of the vector. Now here we not put the comma because these are the columns for the matrix. Now assume that Ax equal to B has a solution. Consistent mean it has a solution. Say x equal to denoted by T1, T2, Tn. So now we have to understand, if we multiple A with X, that how looks like. It is basically we get just multiplying ith column of A with ith component of X, then we add all them. So what we get? So B vector will be then the summation Ti ith component of solution and the ith vector or column vector. So I equal to 1 to n. Say this is 1. Now the claim is here that the column space of A is the same as column space of the augmented matrix. And we know the column space of A means the space generated by this vector alpha 1, alpha 2, alpha n, and column space of A bar generated by alpha 1, alpha n and B. So now it is clear that the set, every vector alpha 1, alpha 2, alpha n is in this set alpha 1, alpha 2, alpha n and B vector. Now you can say that alpha 1, alpha 2, alpha n is in the column space of this, because you can write down this as a linear combination of this column. So clear that the column space of A, the subspace of the column space of A bar. So now the converse, the reverse part of how to do. So now if you see that A vector having column alpha 1, alpha 2, alpha n. So up to this no problem, because here those vectors are here also. The only problem is the B vector. Can we write down B vector as a linear combination of alpha 1, alpha 2, alpha n? Yes, because of the equation 1. So from 1, what we get? We will get column space of A augmented matrix equal to this. So now these two will both imply that the column space of A equal to the column space of A bar. Now therefore the dimension, so dimension will be same because the space are same, so the dimension are same. So the rank of A will be the same as rank of A augmented matrix. So if you have solution, then this condition done. Now if we do the converse part, converse relate that rank of A equal to rank of A augmented matrix, let's say R. So this means the column space of A and column space of A closure will be generated by R linearly independent column. So from here, for rank of A is R, therefore here we will have R linearly independent column. Without loss of generality, we are assuming that first R column are linearly independent. That we can assume because we can interchange the, because commutative property we have in the field, so we can interchange the term with respect to the addition in the equation. So that allow you. So without loss of generality, we can assume that alpha 1, the first R vector, alpha R, this is a basis of column space of A. Now since rank of A closure, not closure, augmented matrix rank is R, and these vectors are inside the column space of augmented matrix of A, so therefore these vectors, and also it is linearly independent, so therefore linearly independent in C of A closure, so this will form a basis of C A closure. So this will imply that alpha 1, alpha 2, alpha R, this is a basis of C of A bar. So since it is a basis, so and B vector is here in the augmented matrix, so this is implies as B vector we can write down as a linear combination of these vectors. So we will have scalar di alpha I vector I equal to 1 to R. So now this we can rewrite that B vector equal to summation di alpha I equal to 1 to R, and after R we will take alpha of, here let's say K vector summation, coefficient we taking 0, K equal to R plus 1 to N. So which imply that this d1 d2 dr, then 0 0 0, this is a solution of the system Ax equal to B. So this is the proof. If the rank of A equal to rank of augmented matrix, then the system is consistent, also the converse. Now in the last part, what we have seen that this give us a clue. I mean not a great clue here that we getting, that to find out the solution here, this give us a clue how to find solution, basically d1 d2. What you have to do, the list that you have alpha 1 alpha 2 alpha, and you have to find out the linearly independent vector. Then B vector you write down as a linear combination of those vectors, then di will give the solution. Now here di you can select in many different ways. If you have only one choice, then we will have a unique solution. If you have more than one choice, then you have infinitely many solutions. So this was the proof basically, for a system is consistent or not in term of rank. So here actually we have done two things. All the thing we have done pure way, without doing any calculation. Yeah, that's all. Thank you.